Welcome back to Cloud 42, I'm James. I have been looking for an electronic lead screw for my lathe for quite some time, and while I've found a few things out there and a couple of commercial products, I haven't really found anything that I felt was really accessible to a hobbyist. And I find lots of people looking for them and not a lot of good information on how to do it yourself. So I've decided to go ahead and develop one of my own. And what you're looking at here is a proof of concept prototype. I've got an encoder connected to a microcontroller driving a stepper motor. And as you can see, I turn the encoder, the motor turns in sync. Right now this is just 1-to-1. Now this is just prototype hardware all thrown together on a breadboard, and the goal here is just to prove to myself that I can make it work end to end. That the microcontroller I've chosen is fast enough, that the encoder is going to work, that I can solve the problems in terms of doing the math and getting the precision I need before I spend a lot of money on hardware like manufacturing PC boards or time on software development for a particular microcontroller platform. At this point, this is all cheap. This is all really easy to change if I run into a problem I can't get past and I have to make major design changes. Once I've spun up PC boards, once I've spent weeks on software development, I can never get that time or that money back. So this is just a quick way to make sure I'm on the right track before I start spending more money and time. But I'm getting ahead of myself. Let's go over to the lathe and let me show you what I'm trying to accomplish. This is my Grizzly G0602 lathe, and this is a great little benchtop lathe. I've been very, very happy with it. It's heavy enough and powerful enough to do serious work, but it's still small enough that it doesn't take up a ton of space, and it's not a huge investment up front. Now, the one thing that has been very frustrating for me on this lathe is the change gears. Now this lathe does have a couple of gear selector knobs on the front here that give you 6 different combinations of speeds. This is not enough for threading. It's generally just used for feeding. So when you have the gears on the end of the lathe here set up for feeding, and this is the feed configuration, this allows you to select feeds anywhere from 2.5 thousandths per revolution up to 14 thousandths per revolution. But if you want to actually thread, you need more variety than this, and you need specific ratios to pull the carriage across for the thread you're trying to cut. And to do that, you have to swap out these gears. The lathe came with a big plastic bag full of these gears, all in different sizes, and you can take this gear train apart and reassemble it in different combinations. And when you do that, you then have to adjust the backlash in the gears, and it's a tedious process. It takes me 10 minutes maybe to tear this down and build it back up, and there's E-clips and little square drives and hex head screws and keys in here, and it's just a tedious process, and it's frustrating. If I'm making a part and I need to thread, and then I need to feed, and then I need to thread, well, I either just get it set up for threading and then just feed manually, or you have to swap this back and forth. And it gets to the point where I don't generally even bother. I'll instead use taps or dies or a thread chaser, something so that I don't have to deal with these change gears. Now I would like to do away with these change gears entirely and replace this all with what's commonly called an electronic lead screw or an electronic gearbox or a virtual gearbox. The idea is we'll take the gears out completely, and instead of driving the lead screw off of a train of gears from the spindle, we'll drive the lead screw with a motor. This is the motor that I plan to use. This is a NEMA 24 stepper motor. This is about 600 ounce-inches of torque, something like 4 Newton meters, and this should be sufficient to drive the lead screw directly without any kind of gear reduction. And I haven't worked out exactly how this is going to fit in here, if I'm going to try to couple it directly onto the shaft, or if I'm going to try to sling it in the back or the front and drive it with a belt. I'll have to figure that out. But ultimately the idea is, without any of these gears, I drive this directly, and then I can, through software in a controller, decide the ratio I want between the spindle and the lead screw and control it directly and virtually. So I just have to change a setting, press a button, and I can change ratios. This will also give me a lot more flexibility for more ratios than I would have with the change gears. Make it easy to switch between imperial and metric threads, for example. Now, in order for this to work, the lead screw has to be synchronized perfectly with the spindle. And when I say perfectly, I mean it's really got to be close, both in speed and in absolute position, so that as you cut a thread, it'll have the same pitch over the entire length, and so that when you go back to make multiple passes on the thread, they line up. Now, to accomplish that, I'm going to use an encoder. This is a little Omron rotary encoder. Looks like a motor, has a little D-shaped shaft on the end of it. And the concept here is that this is an optical device that has multiple, has a wheel in it with multiple slits and multiple optical detectors so that it can accurately produce a train of pulses as this rotates. This particular one is a quadrature encoder that produces 1,024 pulses per revolution, but it's done on 2 signals that are out of phase, so this can actually count 4,096 counts per revolution, which means that if I get it hooked up to the gear train to the spindle so that it's turning at exactly the same speed of the spindle, it can sense the position of the spindle exactly to within 1/4096th of a revolution. And that should be plenty of resolution to keep the screw synchronized with the spindle. So this will feed into a microcontroller. The microcontroller will do all the math and generate the real-time control signals for the motor to run the lead screw, and we'll have a virtual gearbox. No more change gears. Let's talk about microcontrollers. Now, the first platform that most people would reach for a project like this is Arduino. Now, I've got photos here of the Arduino Uno and the Arduino Mega. I've also got some examples here. This is an Arduino Pro Mini. This is something called a DigiSpark, which is an Arduino compatible board that has a little USB connector built right into the PC board. It was a Kickstarter a few years ago. Now, the Arduino platform is really great for most little hobby projects. They're plenty powerful for your typical automation kinds of things, or even, robotics control. But when it comes to real-time control and precision of something like an electronic lead screw that I'm trying to build here, these things really are going to struggle. The encoder I'm using is generating 4,096 pulses per revolution, and you simply cannot miss a pulse. And if the lathe is spinning at a higher speed, 2,400 RPM, and you're generating that kind of pulse train, it is a real challenge for these little microcontrollers, especially the 8-bit ones, to keep up. Now, this is an Arduino Dua. This is a 32-bit ARM-based version, and this would be better. This runs at, I think, 84 megahertz, and it probably has the raw processing power to keep up, but it doesn't have a lot of hardware support for real-time control. We can talk about that a little bit more later, but again, it's powerful enough, but it's going to really struggle to keep up with an encoder and to actually do the floating point math that's required to calculate the gear ratios. So what other options do we have? How about the ESP8266? We've got a Node MCU board that's based on the ESP12 module. Here's a Wemos D1 Mini. These are inexpensive and pretty useful. Got a bare ESP12F module, and here's the ubiquitous ESP01 board. Now, the microcontroller on these is actually quite a bit more powerful than what you would typically see on the 8-bit Arduino platform, and it has built-in Wi-Fi, which is amazing, but it's still going to suffer from the same problem that it's not really designed for real-time control. On the smaller boards, obviously, you have limited I/O options, limited number of pins. But again, it just doesn't have the raw compute power that's really needed to keep up with an encoder, and it has nothing in the way of actual hardware support for decoding the quadrature signals or any of the other stuff that we'd like to have for a real-time motor control system. The other obvious choice to consider is the Raspberry Pi. This is a Model 3B Plus, and it's got a quad-core processor. Of course, it's got Ethernet and USB and Wi-Fi built in. And this is a great little board for lots of applications, but it's not particularly well suited for real-time control. These generally run some variant of Linux, which is a multi-processing operating system. So you've got multiple processes that are all sharing the CPU and being time sliced in and out. And you can do some very powerful stuff. You can run some very high-end software on it, nice big touch screens, great user interface, but they're not particularly good for real-time control when you have signals coming in and you need to respond within microseconds or nanoseconds. You just don't have that kind of time control resolution on these without writing very low-level driver software. But the board I'm planning to use is this one. This is a TI Launchpad. Now, Texas Instruments sells these as a prototyping platform for their microcontrollers. The idea being that once you have your prototype done, you'll actually just buy the chips and put them into your own hardware. But there's no reason that you can't use these boards as a microcontroller. They're not very expensive. This one's about $30. This is the big brother of the one that I used in my initial prototype here. These ones are about $25. And the microcontroller on this is an absolute monster. This thing is a 32-bit processor running at 90 megahertz with lots of flash and lots of RAM. But not only that, the thing is designed for real-time control. It's got a floating point processor unit, so it does floating point arithmetic in hardware, which makes that a lot faster. Plus, it also has something called a control law accelerator, which is a coprocessor for running real-time control loops that can actually run floating point operations in a single clock cycle, which means you can do a floating point multiply in 11 nanoseconds, which is way faster than any of the other platforms that we've looked at. In addition to just being a fast processor, though, this chip has a lot of hardware on board designed specifically for real-time control applications. This has two what they call enhanced quadrature encoder peripherals, which read signals from a quadrature encoder like this in the hardware. So the CPU doesn't have to monitor the pins and count the pulses. That all happens independently of the CPU operation and updates hardware registers. So when the CPU gets around to checking the counters, it can just go look at what the current value is. It doesn't actually have to be in the loop for the counting. And then it also has a bunch of features tied to those encoders for timing analysis. So you can set an interrupt to occur 100 times a second or whatever speed you want, and it will actually grab the value out of that hardware register, copy it into a second shadow register, and then send an interrupt for your software to deal with it. And so you can come along and say 100 times a second, get the actual position of the encoder, and it will be down to the nanosecond. It will actually grab at exactly the same time every time. So you can do things like calculate RPM accurately without having to deal with the jitter of the time that it takes for the microcontroller to respond to the interrupt signal. This has also got a variety of other things. It's got really fast interrupts. It's got again, the latching registers. It's got high resolution pulse width modulators and captures. It's got a bunch of 12-bit analog to digital converters. It can take 3.5 million samples per second. Again, this is just a monster controller for stuff like this. But the thing that really makes this stand out is that over here, this is an emulator, also called a debug probe. So you can take this board with your software running on it, you can connect a USB cable, and you can actually get into it with a debugger, which means you can stop the software at any point, you can go in and look at the values of variables, you can catch interrupts, and as you're trying to develop the software, you can actually have real-time insight into what's happening in the chip, which is something you just can't do with the Arduino platform, at least not with the tools that are available. So this is the board that I'm planning on using, and for 25 to 30 bucks, it's a bargain. Let's talk about user interface. This is the board that I've selected. These are all over eBay, and this is sold as an LED&KEY board. And what it has, it's got an 8-digit 7-segment display. It's got 8 buttons, and it's got 8 LEDs, and the whole thing is controlled over a serial interface. So you need 3 active pins to control this, plus power and ground. Now, why not a touchscreen? Touchscreens are great, and you can make some really cool looking stuff, but I don't personally think it's a great option in the shop. They're delicate, they're easy to break, and I don't know about you, but when I'm working on the lathe, I've always got cutting oil on my hands, and the thought of trying to use a touchscreen and getting that all smeared up just doesn't seem that great to me. On the other hand, these LED displays are nice and bright, they're very easy to read, and having the nice tactile buttons to control things, I think is going to work out better. We'll see in the long run. The idea here is not, of course, to use this thing bare, but to make a 3D printed control panel that goes around this with larger button inserts in it that'll be easy to press. You can either machine it out of, aluminum or plastic, Delrin, something like that, or actually 3D print the front, and then the buttons can be 3D printed, either out of rigid plastic or maybe even flexible material. So we'll have to play with that. The other thing to keep in mind on something like this is these are really, really cheap. I bought 2 of these, and I paid $2 each, delivered. So I've mentioned real-time control several times. Let's talk about what the software in the electronic lead screw actually has to do. So we have an encoder that's generating signals, 4,096 pulses per revolution, and that is going to feed through a hardware peripheral in the chip that is going to feed a count register. Count. And this count will always be the current count of the pulses from the encoder. So as it rotates clockwise, this counts up. As it rotates counterclockwise, this counts down. Now when you take that value, multiply it by some factor, and this factor will change depending on exactly which ratio we're trying to run, which gear ratio we want, which thread we're trying to cut, and that will go into another register, which is the desired position. So this is the desired position of the stepper motor just in terms of count. Now, we will also have to keep track of the current position of the stepper motor. That says current. So we have the desired position of the stepper motor, and we have the current position of the stepper motor, and we have to have some kind of a loop that is constantly generating pulses to the stepper motor to move the current position to the desired position. So in practice, as this is running, the encoder is running freely, and we have to very rapidly check the count on the encoder, multiply by the gear ratio to figure out where we want the stepper to be, and then we have to generate the pulses to move the stepper to that position. And this all has to happen very, very rapidly. Right now in the prototype, I've got this loop running about every 25 microseconds. I make a trip around this loop. And in fact, the loop here on this end is capable of running in 1 or 2 microseconds, so that we can generate the pulse train fast enough, because there's lots of things that have to happen here. If the desired position is higher than the current position, we have to step the motor forward. If it's lower, then we have to toggle the direction line, and then we have to generate steps to go backwards. And there are timing limitations on what the stepper drivers can handle, and so this has to be done very rapidly, but on a very precise timing so that we can generate the signals that we need. And again, this whole loop has to execute very quickly. There's a few other things that can happen. This counter is going to overflow or underflow. This is a 32-bit number, but as it counts up, it'll reach a maximum, and then it'll wrap around to 0. Or if you're going down and it's counting down and it gets to 0, it'll wrap around to the maximum count, and you have to deal with that, or you'll suddenly get a huge step in your desired position, and this loop will then take off and try to run the motor. So you have to detect underflow and overflow and compensate for that and adjust properly. And there's lots of gotchas in terms of losing steps when you do that. This multiplication can be very tricky because standard floating point computation in a real computing hardware is always going to have a representation error, and that error is going to get multiplied as this count increases. The actual position that you end up at can be off. And in fact, in a typical threading scenario, I've done some projections, and if I just use regular floating point arithmetic here, you can end up off by 1/8 of an inch by the time you get to an end of a thread, which is completely unacceptable. Then in addition to running all of this control loop to control the hardware in real time, you then of course have to have the user interface. And so this will be in the control panel. There'll be a bunch of logic that controls, among other things, this factor so that you can change the gear ratio on the fly. There's lots of other stuff it's got to deal with. I want to actually show the RPM of the lathe and use this as a tachometer on the lathe, and I've got several other ideas. So the software, again, the real-time control loop is the really important part, but while it's doing that, it still needs to be able to service the user interface and run the rest of the logic. And that brings us full circle back to the prototype here. Now this is just a little 3D printed tray that I made, because of course I did, to hold the microcontroller and the breadboard and the keypad, just to keep everything together and give me a good place to feed in power. I am running this off of an external power supply right now. It'll eventually run off of a little AC wall adapter. The microcontroller requires 3.3 volts, so I'm bringing in 3.3, 5 volts for the keypad, and 12 volts for the stepper motor. So the stepper driver that I'm using here is in a little Allegro A4988 driver, which is what you would typically see in a 3D printer, though I'll be definitely using a larger 48 volt driver when I'm running on the lathe itself. The other thing that's on this breadboard is a level shifter, because the keypad uses 5 volt logic and the outputs on the microcontroller are 3.3 volts. So the level shifter is here to convert from one to the other. And as you saw earlier, I've actually got this running. Right now this is running 1:1, so it's tracking exactly. And if you want to have some fun, take the video here, slow it down, and see if you can see any discrepancy. At 30 frames per second, I can't find anything. And in fact, when you actually look at this, in general, once the encoder counts, the first pulse to the stepper motor to move it is occurring within microseconds, like single-digit microseconds. So this is going to be plenty fast enough to get the synchronization that we need. Right now, what I have here on the display, the first 4 digits are used for RPM of the motor, or in this case of the encoder. So if I spin it, you can see that's running. The display itself is updating 100 times a second, though I'm only counting right now the RPM I'm only counting it and calculating it 10 times a second. The value over here on the right, this 0.390, is the ratio between the encoder pulses and the stepper driver pulses. The stepper motor is 200 steps per revolution and running with 8 microsteps. So that means that you're running at 1,600 steps for a full revolution on the motor, but we're generating 4,096 steps from the encoder. And so this is the ratio to make them run at the same speed. Now I do have this set up so I can change that. I can press this button and increase it. So we can run this up. In fact, we can run it while it's increasing. You can see it's getting faster and faster up to this ratio. This is just as far as I let it go. So the motor is actually spinning faster than the encoder. And we can run this all the way back down too. Now the final user interface will have specific feeds and threads built in to make it easy to quickly select the things that are actually useful. So let's get a real small number here, and you can see that as I spin this, the motor is still turning, but it's much slower. And this is more like what we'll see when actually using it for feeding on the lathe. Well, this is where the project stands as of today. I am happy with the progress so far, and I think the concept is proved, and now it's time to move forward on hardware and software. Software development, I am doing this open source. The software is on GitHub. There will be a link down in the description if you're curious. Of course, at the moment it's fairly crude, but it'll get better with time. But you can definitely go check that out. I'm also going to be manufacturing a PC board that fits onto the GPIO headers of the board here that has the level shifters to drive the keypad and the optical outputs to drive the larger stepper driver. I don't know if this is something that there's going to be a lot of interest for, or if this is something that I'm just going to make one of for myself. If I were doing it myself, I would make the board on here all surface mount, because I've got a soldering microscope and I can solder surface mount components no problem. But not everybody has that equipment or the patience or the desire to deal with that. And so if this is something that a lot of people would like to build, it would make sense to go ahead and design those boards with through-hole components so that they could be easily soldered from a kit with actual, TO92 transistors and resistors with wires that you stick in the holes and actually solder them. So I'd be very interested in your feedback. If there's a lot of interest, I might actually have some PC boards made that would be good for, hand solder kits. Otherwise, I'll probably go with the surface mount just because it's more elegant and compact. In addition to the hardware and software development, I've also got to figure out how I'm going to hook everything up on the lathe. I've got to mount the encoder. I've got some ideas for that. You can already see I've got a 3D printed gear here that I've been playing with to interface with the gear that's on the spindle. For mounting the stepper motor, I've got some ideas. I'm not sure if I want to do it direct drive or belt drive, but there are some options there. And all of that will be coming up in the future. In the meantime, I would love to hear from you. Leave your thoughts and suggestions down in the comments. If you like this sneak peek into my R&D process, give the video a thumbs up and feel free to subscribe so you don't miss future videos. Thank you for watching.